Hello and welcome back to yet another episode of Computer Graphics. Myself, Fazira Razak Hamza, Assistant Professor, PG Department of Computer Science, and I am here to present on the course Computer Graphics. So, in the last episode, we have completed Unit 1 and I am moving on to second unit in CG, that is 2D graphics. So in 2D graphics, we are going to see or discuss on points and lines. Point plotting is accomplished by converting a single coordinate position furnished by an application program into appropriate operations for the output device in use. With a CRT monitor, the electron beam is turned on to illuminate the screen phosphor at the selected location. A random scan system or vector system stores point plotting instructions in the display list, and coordinate values in these instructions are converted to deflection voltages that position the electron beam at the screen locations to be plotted during each refresh cycle. Line drawing is accomplished by calculating intermediate positions along the line path between two specified endpoint positions. An output device is then directed to fill in these positions between the endpoints. For analog devices such as a vector pen plotter or a random scan display, a straight line can be drawn smoothly from one endpoint to other. Digital devices display a straight line segment by plotting discrete points between the two endpoints. Discrete coordinate positions along the line path are calculated from the equation of the line. So, this is the line drawing algorithm. Okay, we have the Cartesian slope intercept equation for a straight line, that is y is equal to mx plus b, that we have studied it in the small classes, right? Equation of straight line is y is equal to mx plus b, with m representing the slope of the line and b representing the y-intercept. Okay, given that the two endpoints of a line segment are specified at positions x1, y1 and x2, y2. Let's see. So, this is the y and this is the x-intercept. We have x1 and x2 on x-intercept and y1 and y2 on the y-intercept. Okay. Now, figure shows the line path between endpoint positions x1, y1 and x2, y2. Now, we can determine the values for the slope m and y-intercept b with the following calculations. See, slope m can be defined as y2 minus y1 divided by x2 minus x1. And y-intercept b is equal to y1 minus m into x1. That we are calculating from the straight line equation y is equal to mx plus b. Okay. I hope it is clear. And we have the delta y as y2 minus y1 and delta x as x2 minus x1. In principle, we would like the sequence of pixels to lie as close to the ideal lines as possible and to be as straight as possible. Okay. A scan converting lines. A scan conversion algorithm for lines computes the coordinates of the pixels that lie on or near an ideal infinitely thin straight line imposed on a 2D raster grid. So this is a 2D raster grid. Here the figure shows a highly magnified view of one pixel thick line and of the ideal line that it approximates. The intensified pixels are shown as filled circles, that is black circles, and the non-intensified pixels as unfilled circles. Since sRGB parameters are defined on an integer grid, the endpoints of a line have integer coordinates. So we can only plot integer coordinates for a line to scan convert. Now we'll see what is the simple strategy for line scan conversion. The simple strategy for scan conversion of lines is to compute the slope m as delta y by delta x and to increment x by 1 starting with the leftmost point and to calculate yi is equal to mxi plus b for each xi and to intensify the pixel at xi comma round of yi. This computation selects the closest pixel, that is the pixel whose distance to the true line is smallest. This strategy is inefficient. Why? Because each iteration requires a floating point multiplication and addition. We can eliminate the multiplication by noting that yi plus 1 is equal to mxi plus 1 plus b, right? Since we have the straight line equation, y is equal to mx plus b. So, yi plus 1 is equal to mxi plus 1 plus b. Which means m into xi plus delta x. A unit change in xi means xi plus delta x plus b, which is equal to mxi plus m delta x plus b, which means mxi plus b is yi, right? So, yi plus m delta x. And if delta x is equal to 1, then yi plus 1 equal to yi plus m. Thus, a unit change in x changes y by m, that is slope. Therefore, for all points xi, yi on the line, if xi plus 1 equal to xi plus 1, then yi plus 1 equal to yi plus m. So, this defines an incremental algorithm. This is the basic incremental algorithm or DDA. DDA means Digital Differential Analyzer. DDA is a mathematical device that solves differential equations by numerical methods. When m is between -1 and 1, that is the slope is between -1 and 1, xi plus 1 is equal to xi plus 1 and yi plus 1 is equal to yi plus 1, what we have seen now. When m is outside these limits, that whether m is greater than 1 or less than -1, yi plus 1 is equal to yi plus 1 and xi plus 1 is equal to xi plus 1 by m. Algorithm takes an incremental approach in order to speed up scan conversion, that is, when the slope of the line is between -1 and 1, begin at the first point and increment the x coordinate by 1 and calculate the corresponding y. That is, yi plus 1 is equal to yi plus 1 m. When the slope is outside these limits, increment the y coordinate by 1 and calculate x by xi plus 1 is equal to xi plus 1 by m. Now we'll see the algorithm. That is, first we are doing a C version of the algorithm. So it is hash includes device.h. Now we are defining a function known as void line with x0, y0 as the left endpoints, x1, y1 as the right endpoints, then a value to store the intensified pixels. Then we are defining an x variable. Then we are defining delta y, that is y1 minus y0, delta x, that is x1 minus x0, and slope of the line, that is delta y by delta x. Then we are assigning the left endpoint y0 to y. Now we are putting a for loop where x less than, or we have to do the conditions till x less than or equal to x1. What are the conditions? We are writing the pixel x comma round of y to the value, and we are incrementing y by the slope m. So this is how we plot a line. Okay, blue filled dots represent that they are the pixels which are intensified at the particular positions. But see, the line does not move through the intensified pixel because we are finding the very closest pixels, intensified pixels of the line. So the DDA algorithm is faster than our previous simple method. There is no multiplications involved. But there are some disadvantages. That is, we are rounding here, right? We are rounding the values of y. So accumulation of round off errors can make the line drift from the true line. Then rounding off and floating point arithmetic involves time. See here, write pixel is a low-level procedure provided by the software. It places a value into a canvas for a pixel specified in the coordinates, which is given as the first two arguments. Now I'll move on to the next algorithm, that is Bresenham's midpoint line algorithm. So we saw a simple strategy for line algorithm, then we saw a DDA or digital differential analyzer algorithm for line, and now we are going to see Bresenham's midpoint line algorithm. It is developed by Bresenham. It avoids the rounding of function and uses only integer arithmetic. Now let's take a look on the figure. We have a previous pixel. So we have choices for current pixel and choices for next pixel. The previous pixel is stated as XP, YP. Here we have a midpoint stated as M, and we have options for choosing between east and northeast pixel, that is E and NE stated in the figure. Now assume that the line slope is between 0 and 1. The lower left end point is x0, y0 and upper right end point is x1, y1. We have selected the pixel P, XP, YP. Now we have to choose between the pixel one increment to the right. See, take a look at the figure. One increment to the right one increment to the right, that is east pixel, or one increment to the right and one increment to the up, that is northeast pixel. Now let Q be the intersection point of the scan converted line with the grid line x is equal to xp plus 1. So I have marked a Q here. In Bresenham's calculations, the differences between the vertical distance from E and NE to Q is computed, and the sign of the difference is used to select the pixel whose distance from Q is smaller. In midpoint calculations, we check on which side of the line the midpoint M lies. Okay, if the midpoint M lies between the line, northeast pixel is selected. So if it is below the line, midpoint is below the line, northeast pixel is selected. Now, if the midpoint M lies above the line, the pixel E is chosen. So, if midpoint is below the line, northeast pixel is chosen. Above the line, east pixel is chosen. Now, let's represent the line by the function f of xy equal to ax plus by plus c is equal to 0, which is marked as equation 1. We have already know the equation of the straight line, Cartesian equation of the straight line, that is y is equal to mx plus b. Y is equal to dy by dx into x plus b, that is m is dy by dx. Now dx into y equal to dy into x plus b into dx. We are multiplying dx throughout the equation. Then we get dy into x minus dx into y plus b into dx equal to 0. That is marked as equation 2. Comparing the coefficients of 1 and 2, we get a is equal to dy, b is equal to minus dx, and c is equal to b into dx. So f of xy equal to 0 when it is on the line, positive when it is below the line, and negative when it is above the line. To apply the midpoint criteria, we need to compute f of m, that is f of m is equal to f of xp plus 1 comma yp plus half, because half of the line the midpoint is there. So if y coordinate is only half of the line, that is yp plus half. Okay. Now we define a decision variable d. d all is equal to f of xp plus 1 comma yp plus half, which is equal to axp plus 1 plus b into yp plus half plus c. Now we have case 1, that is if E is chosen. If east pixel is chosen, M is incremented by y in x direction. So d nu is equal to f of xp plus 2. Only x is incremented by 1. So xp plus 2, yp plus half. We are putting it into the equation a xp plus 2 plus b into yp plus half plus c. Then d new minus d old, we get, see, axp and minus axp get cancelled, that is marked as blue, and byp and minus byp is marked in red, they also get cancelled. Half b and minus half b is marked in green, they are also cancelled. C and minus c is marked in pink, they are also cancelled. Remaining is 2a minus a, which is a. Okay, so the increment to be added to d after E is chosen can be written as delta E is equal to a, which is equal to dy. So we already know that a is equal to dy. Then case 2, if northeast pixel is chosen, M is incremented one step both in x and y direction. So the equation becomes f of xp plus 2 comma yp plus 3 by 2. 1 by 2 plus 1 is 3 by 2. Then we will define a d new for that, a into xp plus 2 plus b into yp plus 3 by 2 plus c. d new minus d old. See, the unlike terms are being striked out, and remaining is 2a plus 3 by 2b minus a minus half b. So 2a minus a is a and 3 by 2b minus half b is b. We get the answer a plus b, that is dy minus dx. Therefore, the increment to be added to d after northeast pixel is chosen is delta ne is equal to a plus b, which is equal to dy minus dx. So now if d is greater than 0, choose the pixel northeast, and if d is less than 0, choose the pixel east. If d is equal to 0, either east or northeast pixel is chosen. The location of M and the value of d for the next grid line depends on whether east or northeast pixel is chosen. So the first pixel is the first endpoint, that is x0, y0. The first midpoint is at x0 plus 1, comma y0 plus half. That is ax0 plus 1 plus b into y0 plus half plus c, which is equal to ax0 plus by0 plus c plus a plus b by 2. Is that okay? We are expanding the terms. Now f of x0 y0 plus a plus b by 2, because ax0 plus by0 plus c means f of x0 y0, and the remaining terms a and b by 2. Since x0 y0 is the point on the line, f x0 y0 equal to 0, so we can calculate a d start, that is a plus b by 2, okay, which is dy minus dx divided by 2. To eliminate the fraction in d start, multiply the function by 2, that is f of xy equal to 2 into ax plus by plus c. So this does not change the sign of the variable d. Okay. The incremental midpoint technique chooses between two pixels based on the sign of the decision variable calculated in the previous step. Then it updates the decision variable by adding either delta E or delta NE. Now let's take a look on the algorithm. We start with hash include device.h. Then we define a midpoint line function with x0, y0, x1, y1 and a value. Now we are calculating delta x, delta y and a d start, which is 2 into dy minus dx. Then delta E as increment E, that is 2 into dy, and delta NE as increment NE, that is 2 into dy minus dx. Then we are assigning x0 to x, y0 to y, and we are defining a right pixel, that is the start pixel. We are writing it to the value, that is x comma y. Now we have to do it up to while x less than x1. First we'll choose E. If we are choosing E, that is d should be less than or equal to 0. Then we are adding delta E to d. Then we are incrementing only the x coordinate. Else when we are choosing delta NE, we have to add delta NE to d and we'll increment x and y. Then we will write the intensified pixels to the value, close the while loop, close the midpoint line loop. Okay, this is the algorithm for Bressenham's midpoint line algorithm. Now I'll see a simple problem on how to calculate pixel for a lines using midpoint line algorithm. See, this is the question. Calculate using midpoint line algorithm the values of decision variable d and the resulting selection of the pixels of a line from 5, 8 to 9, 11. So the solution is we have given x0, y0, that is 5, 8 and x1, y1 as 9, 11. First we'll find out delta x, that is x1 minus x0, that is 9 minus 5, which we get the answer as 4, and delta y as y1 minus y0, that is 11 minus 8, we get the value as 3. So we have delta x as 4 and delta y as 3. Now I'll calculate delta NE, we get minus 2 and delta E as 6. Okay. First we'll find out the d value. Depending on the d value only we can move further in the problem, right? So d, for now we are getting the d value as 2. 2 means it is greater than 0. So we are choosing delta NE and check for the condition whether x is less than x1. Here 5 is less than 9. So we can move forward, right? We can only do the calculations until x less than x1. Okay. So we are adding delta NE to d. So we are adding minus 2 to 2, which becomes the new d value as 0. Now since we have added delta NE, we will increment both x and y coordinates. So now 5, 8 will become 6, 9. Now D is equal to 0, then we'll choose delta E. So we'll add 6 to 0, that is, now the D becomes 6 and we'll only increment the X coordinate. Now 6, 9 will become 7, 9. Okay, now the new D is 6, so we have to choose delta NE, which is greater than 0, and check for X less than X1, that is 7 is less than 9. So we can add delta NE to D, that is 6 plus minus 2. Now the D becomes 4, and we'll increment X coordinate and Y coordinate. Now the pixel 7, 9 will become 8, 10. 7 plus 1, 8, and 9 plus 1, 10. Now the D is 4, so we have to choose delta NE. Again, we'll add delta NE to D, that is 4 plus minus 2. We get the new D value as 2. Now we have to perform X plus plus and Y plus plus. Now 8, 10 will become 9, 11. Now we can stop because X is not anymore less than X1. Now X is equal to X1. So we are stopping here. And we have got the endpoint, that is 9, 11. Now the points we plotted are 5, 8 is X0, Y0. Points we plotted are 6, 9, 7, 9, 8, 10 and 9, 11 is the X1, Y1 value. So this is the rectangular grid where I can draw the line. I'll plot the first point on 5, 8, that is X0, Y0. Okay. Next point on 6, 9, that is the next plotted intensified pixel, that is delta NE. Then the next intensified pixel is on 7, 9, that is delta E. Then the next intensified pixel is on 8, 10, that is delta NE. And the last pixel is on 9, 11. Okay, I'll draw the line. So there are two pixels which are not on the line. They are the closest pixel to the true line, but we cannot connect the line through the pixels. Thank you. Thank you so much for listening.